So good afternoon, everybody. I hope everybody is okay. And we have today another seminar from the Group of Orbital Dynamics and Planetology. And now we have the pleasure to have here Matías Cerioni. Matías got his degree in Licenciatura in Astronomia from the Universidad Nacional de Córdoba, Argentina. His licenciature thesis was on comparison of orbital and physical parameters of planets in binary stars and single stars. And in 2021, he started his PhD in the Observatório Astronômico de Córdoba, and he is under the supervision of Christian Bourget. So, Matías, it's a pleasure to have you here. So you can share your screen now.
Mm-hmm. Okay, thanks. I'm sharing the screen right now. And let me see when the full screen is on.
Okay, it's perfect. You can start, please.
Okay, well, thanks. A few of you may be familiarized with this presentation because I gave it in the Talier, but I try to add some new stuff and also make it a bit longer. But yeah, as he just said, I am making my PhD in Córdoba under the supervision of Christian Bourget. And I want to tell you about this recent work we published about the planetary system K2138. K2138 is a very compact system of 6 low-mass planets with periods ranging from 2 up to 40 days. Now, what's most interesting about this system is that its very high multiplicity brings with it a very rich dynamical structure. And that is that the system is riddled with mean motion resonances. To start off, we have the first 5 inner planets in very near a successive chain of 3 true mean motion resonances. This is followed by a very wide gap that separates the 6th planet. Notice that this last period ratio is of 3.29, which is more than twice that of the previous ones, which were of almost 1.5. And I say almost 1.5 because the planetary pairs do not fall exactly on these resonances, but they appear to have this little offset, which actually seems to increase with semi-major axis, curiously enough. We will come back to this in a few slides. But apart from the 2 planet mean motion resonances, which I will add that these are just these relationships, these commensurabilities between the periods of the planets, we also have these resonances, these relationships between the periods of the planets among planetary triplets. We have these 3-body mean motion resonances. For example, we have the 253 resonance between the first triplet, and we also see this resonance among the second planetary triplet and the third. So we have this curious structure of a clockwork inner system with a long and dense chain of 2 and 3 planet mean motion resonances, followed by a 6th planet, which is apparently disconnected and not participating in any of that. So this gap clearly strikes out and brings forth the question, which planetary formation mechanisms can make such orderly or so many orderly clockwork-like planets and also separated planets at the same time, you know? Well, in answering these questions, we at least know that the planets did not form how we see them, probably. That is because migration has to have played a role. Let's remember that migration happens because planets do not form in a vacuum, but they form in a disk. And just so happens that orbiting through a gas disk, a protoplanetary disk, is not free. What happens is that while in orbit through the gas, the planet disturbs the disk, generating gas density waves. These gas density waves in turn exert a torque on the planet, which causes the planetary migration, which is usually just spiraling down towards the star. Here we can see a video made by Pablo Benítez Chambay, which is an ex-member of our group, who is now in Chile, where we have a planet orbiting through the gas, and he's generating these waves as he falls in a spiral. Notice that the initial orbit was this yellow dotted line, and he's slowly spiraling down. So we know that when planets form, they do so in protoplanetary disks, and as they orbit, they are affected and the positions change. So why is the sixth planet separated from the inner system? Well, these first few hypotheses involve migration, but they are the closest thing to saying because they formed that way. Maybe the sixth planet formed near the inner system. They all formed together, but because of their masses and because of planetary migration, it suffered divergent migration, separating slowly from the inner system, moving at a different rate, until the protoplanetary disk dissipated, and then it just stayed there. Or maybe the sixth planet formed farther away, and it suffered a quick convergent migration, getting ever closer to the inner system, up until the gas dissipated. Now, we did study these scenarios, but found that these are not favorable given the estimated masses, but we do not outright reject them if we allow for a certain flexibility in the planetary masses and the disk parameters as well. Now, what I'm most interested in telling you about in this presentation is a different hypothesis, and that is that the sixth planet is actually not separated from the inner system, but that it is actually a part of a six-planet resonant chain. Now, to go deeper on this hypothesis, we need to familiarize ourselves with plots such as this one, which is separation space, in which we take one planetary triplet, that is 3 planets, and we plot its period ratio between the inner pair on the y-axis and the period ratio between the outer pair of the triplet in the y-axis. Now, again, I'll just remind everyone that 1 point corresponds to 3 planets. Now, separation space is great to study dynamics because we can plot as vertical lines, or we can mark as vertical lines the 2 planet resonances between the inner pair, and as horizontal lines the resonances between the outer pair. We can also mark as diagonal lines, such as this one, 3 planet resonances which involve all 3 planets. Now, if we go back to the triplets of K2138 of our planetary system, we have this. These 3 triplets, these 3 points, correspond to the 5 inner planets, which, as we mentioned, are very close to the 3-2-3-2 resonant chain, which would be this right intersection of the 3-2 versus 3-2. But these first 5 inner planets are also on top of this 3-planet resonance, the 253, which is the one we mentioned a few minutes ago. Now, the last triplet involves the last planet, which is much further away in the y-axis due to that infamous gap separating the 6th one. Now, the interesting part comes when we closely study the region around this last triplet, and we found a few other resonances. Here we have the zoomed in area, and we can see that the last triplet falls suspiciously on top of the 243 three-body resonance. Now, this is very interesting because you can sum up the indexes of this resonance, and you will see that this is a first-order three-body resonance. This is a resonance of order 1. This is very interesting because first-order three-body resonances are usually very weak, and because of this, no other first-order three-body resonance has been identified in a real system before, so far. So this would be something very interesting to confirm. Of course, just having the triplet fall on top of this resonance is not enough to confirm that the system is actually dynamically linked with this resonance. We need to corroborate that a capture in such a weak resonance is even possible. And that's what we attempt to do in this work. That's the core of our work, trying to find out how did it get there, and if the capture is even possible. Now, to try to confirm this capture, or to try to see if this capture is possible, we follow a migration story for the system, which is actually suggested by this same plot. Spoiler alert, what we try to confirm is that, or what we propose, is that the triplet arrived at this right intersection down here, and then escaped over the three-body resonance. That's what we propose that happened. That's what we think that happened. Now, let's go a bit deeper into that migration story. It's basically a migration story in 2 phases. The first phase has to do with the protoplanetary disk. Now, let's take a random triplet, an arbitrary triplet with some given initial separations, which is this white dot. Now, because of the protoplanetary disk, the planets will migrate, and if the masses are favorable, they will have a convergent migration. This will move this point towards the lower left corner until it bumps into a right intersection such as this one, where it will stop because the 3 planets will have formed a chain. They have formed a chain, so the relative separations will no longer evolve, and the point will just stay there. Now, after a few million years, the gas disk will dissipate, migration will cease, and other weaker effects can take place, such as tidal interactions between the planets and the star. Now, previous works have shown that tidal effects tend to open up these triplets, tend to separate the planets, and that they usually do so by escaping this intersection, the right intersection. Moreover, they usually escape the intersection by following a 3-body resonance, meaning these diagonal routes. Now, if we check again the triplets in K2138, we see that every triplet suggests a migration story such as this one. Every triplet here suggests that it first arrived at a right intersection and then escaped over a 3-body resonance. And that is what we try to corroborate with simulations. So that's our method, to simulate first the migration phase, where we will see the formation of the 2 planet chains. And then the second phase, where we simulate the tidal evolution or the tidal interactions between the star and the planets, and which should show this escape over the 3-body resonances. Now, let's quickly go through our results on both phases. We start with phase 1, where we assign some initial relative separations for each planet, and just let the system migrate with the protoplanetary disk. Now, down here we can see the inner system, the first 5 planets. These are the triplets. And we can see that they successfully arrive at the 3-2-3-2 intersection, meaning that the inner 3-2 chain formed. Now, what we are most interested in is actually the last triplet, for which we considered two different cases up here with different initial relative separations and different planetary parameters and disk parameters. And what we can see is that both sets actually seem to converge to the 3-2-3-1 intersection. I will note here that this scenario, which we proposed, also involves a new two-planet resonance, which is the 3-1 resonance between the last pair, between planets 5 and 6. But apparently, well, as I said, the inner planets converge to the 3-2-3-2. The outer pair, both cases, converge to the 3-2-3-1. Well, yeah, both successfully have arrived at the 3-2-3-1 intersection, but this is still not enough to confirm the capture. We actually have to check the resonant angles. That's how we confirm that a planetary pair or triplet is actually in resonance. So if we check the resonant angles, we can see that effectively every planetary pair has arrived at their respective resonance as expected. Even the last planetary pair arrived at that 3-1 resonance, which is actually a weaker resonance because it is of order 2. But nevertheless, one of its resonant angles, which is in fact the red one, at some point does start to librate, and this oscillation is even maintained even after the protoplanetary disk dissipates, a moment which we mark with a vertical line. So what we are seeing here is that through planetary migration, the system has formed a 6-planet chain. In fact, the 6-planet 3-2-3-2-3-2-3-2-3-1 chain. Okay. Moreover, phase 1 has also seen the capture of the last triplet in the 2-4-3, as we can see here. So a capture in that first order weak resonance has actually occurred. But nevertheless, every planet, every pair, and every triplet is still far away from its current separations. Okay. So, well, that takes us to phase 2, where in phase 2 now the protoplanetary disk has dissipated. So migration has ceased, and weaker effects such as tides can take place, in which we consider the tides produced on the star and on the planets. Now, let's remember that tidal effects are more relevant near the star, and in fact, our results are indistinguishable from the fact where the only planet interacting via tides was actually the first one. We tested both cases, and both are indistinguishable. So we can assume from now on that every result that I will show you is due to the tidal interaction between the star and only the first planet. Now, we will also remember that in systems such as these ones, tidal effects usually cause the semi-major axis to drop, and this will open up the first planetary pair because the first planet is getting farther away. And this splitting up, this opening up, is actually what will produce every change or every result or every evolution that I will show you just now. What we're seeing now is probably the most important plot of the presentation, like the main plot of the presentation. This is a GIF of phase 2. As I said just then, tidal effects are opening up the first planetary pair because the first planet is falling inwards. Nevertheless, the opening of the first pair is actually causing every component of the system to also be affected. As we can see here, every triplet is opening up. Every planetary pair and every planetary triplet is opening up, and they do so by escaping or following the 3 planet resonances, which are these diagonal curves, as we expected. What's most interesting is that all of them seem to arrive at the black points, which are the real separations, their current separations, at the same time. Again, every element is opening up, is being affected. The whole system is like, or every separation is expanding, and they simultaneously arrive, all 6 planets, at their observed separations. And what's more is that the last planetary triplet, which is the green one in the right, does actually follow the 2-4-3 resonance. So apparently this weak resonance can affect very importantly the system, this real system, and actually take the last triplet to its observed separation. I will repeat that we obtain these results for different planetary parameters and disk parameters as well. I will also repeat again, because I feel that it's very important, that this global evolution of the system is happening only because the first planetary pair is opening up. But why exactly is this? Well, let's remember that tidal effects are making the first planet fall inwards, and this will open up the first pair. But what else is going on? Well, let's remember that the planets are in chains of 2 and 3 body resonances. And in fact, it's actually the 3 body resonances, the 3 body resonance chain, which puts them in this sort of lock mechanism, or we call it elevator door mechanism, where opening up 2 nodes causes every other node to also open up. Also making, at all times, making sure to stay on top of the 3 body resonances. So that's what's causing the global evolution. Here we have another GIF of phase 2, where we can see what's happening exactly with the orbits. Now, I mentioned that every separation is increasing, every relative separation is increasing, because the triplets were moving towards the upper right. That means that the planets are increasing their separation. But we can see here that, in fact, even though the separations are increasing, not every orbit is expanding. In fact, most of them are actually shrinking as the separations increase. This is not the case, though, for the 6th planet, which actually goes outward, and the 5th planet, which curiously enough seems to stay in place. Here, for example, we can see a plot of how the semi-major axes have changed for each planet in this interval, and they change up to 4% in value. But well, I want to make one last comment about this weird offset ordering or offset effect that I mentioned at the start, which is that as we see the system today, the first 5 inner planets do not seem to fall exactly on the 3-2 chain, but they have these offsets which seem to increase with semi-major axis. I just want to add that this is not mystery at all in our model. This is actually just a geometric consequence of the slopes of the 3 body resonances involved, as we can see here. I go to through the conclusions of this part of the work. The presentation doesn't actually end here, but well, What's probably most important about this work, is just to mention that we were lucky enough to observe that the last planetary triplet seems to fall on top of that special resonance. So we proceeded to corroborate numerically if a capture in such a weak resonance was even possible, and we did so with a migration history of two phases. First, the system through planetary migration arrives at the 6-planet chain, the 3-2, 3-2, 3-2, 3-2, 3-1 chain, and then is followed by escapes over the 3-body resonances due to tidal interactions between the star and only the first planet. If confirmed, this would be very interesting because this would mark the first evidence of a pure first-order 3-planet resonance in a real planetary system. Now, this also opens some new doors as well, some new questions. For example, maybe this is a bit hard to read, but having found basically by chance that this triplet falls on top of this first-order resonance, suggests that these resonances are probably more frequent than we thought. And well, this seems to be the case, as we have made up a list of some systems which suggest dynamical links with these types of resonances. We do not expect all of this to have a dynamical link with these resonances, but we have to study them a bit deeper. There's also room to dig on the dynamical consequences of having this special resonance on a system with so many planets. Like we did start to see some weird things. For example, in phase 2, when they are escaping over the 3-body resonances, the eccentricity of the last planet actually seems to increase significantly, which is quite interesting. And also, and probably the question that bugs me the most, is why do this triplet prefer this first-order resonance, the 2-4-3 resonance? Like, why does it get captured here instead of the 4-7-3, the 0-order one, which is right next to it? Like, this should be a stronger resonance in principle, although one needs to do some math to confirm that it is stronger. It certainly doesn't seem so, because the triplet gets captured in the first-order one right next to it. But why is this? But well, these are some questions that we wish to attack in future works. In fact, I will show in a minute some work that we are doing to address the third question. But first, let me take a brief detour, an appendix. Have patience with me, but I do want to take a minute or two to talk about how it is my personal opinion here that K2138 is now the most musical system that we know of. This sounds weird, but have patience with me, please. Well, it has to do that music is also about frequency ratios. Like, if we have two people singing at different frequencies, this choir will sound harmonious if the frequency ratio is also similar to a low integer ratio. Low integer ratios sound good in frequencies. In fact, our music scales, the root, the second, the third, the fourth, these intervals which make up our music scale are composed of frequency ratios, which are low integer ratios and which are reminiscent of mean motion ratios, meaning the resonances, the two-body resonances that we just commented about. And the most important interval in this music scale is the perfect fifth, for a few reasons. The perfect fifth is often, among many cultures, the first music interval discovered, because it's the one that sounds most harmonious to the ear. In fact, from the fifth interval comes the circular fifth, which was developed again independently by many cultures. And the circular fifth is where we get the 12 Western notes. So if we go back to K2138, we saw that at some point in its history, it went through this two-planet chain, or six-planet chain of two-planet resonances. It went to the 3-2, 3-2, 3-2, 3-2, 3-1 chain. Well, considering what I just said, this chain is made up of four successive fifths, and it has a new 3-1 which strikes out. Now, what is the 3-1 in this context? Well, it happens that the 3-1 is also actually a fifth, because a factor of 2, as in this case, only moves you up an octave. No, it's the same key, but so it's a bit higher, you know. So what we actually end up having is actually a chain of 5 successive fifths. So we see that K2138 at some point in its history went through this chain of 5 successive fifths, a system made up of fifths, you know, which I hold that is the most important musical interval. And this is very fun. Oh, this is in Spanish. But, this is very fun because this is reminiscent of this philosophical movement, the harmony of the spheres, where they try to find these relations between the distance or the movements of the planets and musical intervals. And this would be the case, wouldn't it? Well, to highlight this a little bit, I wrote a little Python code to try to play what this would sound like. And here is where I need to know if you can listen to audio that I reproduce here or no. So let me see. I will try to play this in 3, 2, 1. Could you hear that?
Yes, yes.
Yeah?
Yes, yes, very nice.
Thanks. What we heard there were 6 frequencies, which had these relationships among them. The frequencies had a factor of 3-2 over them, or 3-1. They were 5 successive fifths. As they are getting successively captured, they create this choir, this harmony, which should sound very harmonious to the ear. I'll play it one more time so we can hear it with context. Okay, and over here, as a follow-up, I wanted to see what would phase 2 sound like, because what I just played you there is just the 2-planet chain, not the 6-planet chain, but the 2-body resonance chain, you know, the 3-2, 3-2, 3-2, 3-2, 3-1 chain. But in phase 2, the planets actually get away from that configuration and they escape over the 3-body resonances. There, the frequencies change. So how does it sound when the frequencies themselves change? well, this is how it will sound. What we will hear here is first the captures, and then after that, how the frequencies change as the planets escape over the 3 baryresonances. Well, that's it. For a moment there, it seems like it's gonna keep going until the computer explodes, but it's not. But it doesn't sound as harmonious as perfect fifths, as 2 planet resonances, but I still feel it's cool. But well, yeah, basically in summary, the most important musical interval is the fifth, and K2138, at least at some point in its history, seems to have been made up of only fifths, and it's 5 fifths. It's a lot of fifths. It's like the most harmonious choir, which would sound to the human ear. Okay, now next I want to show a few steps that we are taking towards answering the third question. Why do triplets get captured in this first order resonance instead of the 0th order resonance right next to it? I will just make a warning that this is a very work in progress, and what I will show many simulations of what we are doing and what we are obtaining. But yeah, the question as we frame it, or at least when we think how we can attack the problem, we started attacking it this way, answering which planetary and disk parameters favor the capture in this weird resonance. Well, this chapter will be also characterized by a lot of simulations, like how many simulations can we throw at the problem until it solves itself. Warning, there are also other important things to do to attack this question, such as the analytical way of writing the right Hamiltonian and studying the resonant widths and such. We are doing that, but we still don't have such pretty results. So right now I will show you the results of exploding your computer towards a problem. And we will start by a simpler case. This time we are not considering 6 planets. We are considering just 3 planets which we want to capture in these weird resonances. So we take 3 planets of 8, 9, and 10 Earth masses, and we just jump right to it. We fix a few initial parameters, well, other than the masses. For example, we fix the semi-major axis of the 3rd planet at 1 astronomical unit, and we place it on some point. We place the triplet on some point on this plot, like here, and just placing it here fixes the initial relative separation of the inner pair and the outer pair. So because we also have fixed the semi-major axis of the 3rd planet, we can calculate the semi-major axis of the rest of the planets. We also give, well, circular orbits, initial circular orbits, and we give very little inclinations. This is actually an advice from Tatiana Michenko, as given to me through Christian Bauchet. Christian says that Tatiana says that you should also give a very little inclination, just in case that there is some weird effect that bumps the inclination all the way up. But well, we also give some standard disk parameters for the density, for the power law exponent, for the aspect ratio and the flare. We are considering, for example, a a flat disk. And we just let these 3 planets migrate. We can see in the plot on the left how it migrates, starting from the red little box. It clearly goes downwards and to the left until it bumps into the 3-2 with a certain offset, this margin. But it keeps going downwards until it gets captured into the 243. This is the 243. I forgot to put a label on it, but the red dotted line is this weird resonance which we are interested in. Well, from a few other simulations, we know that initial separations, the position of this little box, is actually important. For example, as we can see here, the initial separations can have different results. For example, in the left plot, which is the one that we just saw, I painted the box red because it got captured in the 243. In the rightmost plot, which is the same system but with a different initial separation between the planets, I painted it blue because, as we can see, it does not get captured in the 243. It just keeps going downwards. And in the middle case, in the middle plot, we can see that only changing the relative separations, that means the location of the box. Well, in this case, what we see is a temporary capture. That you can see that it comes into a little bit of the 243, travels a little bit over the 243, but then falls down. So we paint it red and then blue as a temporary capture. So unexpectedly to us, initial relative separations do matter. The initial position of this box in this plot does matter. So what we proceeded to do was a grid of migration paths, and as we can see here. What we see here is a lot of migration paths, a lot of boxes. But we can see that there seems to be three domains. We can see a capture region, which are the red boxes on top, which are systems which got captured in the 243. We can then see an interface over here of temporary captures, and then a big escape region of systems which did not get captured in the 243 and just kept going downwards. So apparently, again, relative positions do matter, and there is a capture region and there is an escape region. What's very interesting that we didn't get here is that there is no sign of capture in the 473. That is in the theoretically stronger resonance, which is right next to it. There's something special with the 243, apparently. Well, maybe something that we thought could explain this behavior or this separation, maybe it's got to do with the eccentricities of the planets as they cross the 243, in this moment. This was actually something suggested by Tabaré Gallardo. I remember on the taller, he made me a question about this. Well, we did study the eccentricities at the moment of crossing. For example, this is way too small, but all three plots mean the same. We basically have the eccentricity of the first planet here on top, the eccentricity of the second planet, and the eccentricity of the third planet here. And we show the evolution for 4 systems. In blue and light blue, we have capture systems. That is system, or this, yes. I could have swapped the colors now that I think about it, because back here I'm using red for capture, but never mind. Blue systems here are from the capture region, are systems which did get captured in the 243. And red and orange systems are escape systems which did not get captured in the 243. And what we have in the, again, we are analyzing their eccentricities as they evolve. And instead of time in the x-axis, I put the period ratio between the outer pair. That is, notice how every system falls vertically down here until it crosses. So I want to see at this y value, when it crosses the 243, what are the eccentricities at this y value. So I plot the eccentricities versus the y value, and the crossing y value is this vertical line, black line, and I can see that before crossing the 243, I do not manage to see any difference in any of the eccentricities, not in the eccentricity of the first planet, or not in the second, and neither in the eccentricity of the third planet. I notice no difference between blue systems and red systems. So eccentricity does not seem to be the whole story, at least. Maybe it has to do, maybe it has an effect in a previous step in the evolution or something like that, something a bit more indirect, but it does not seem to be the whole story. But one takeaway that we can get from this grid is that apparently a bigger initial separation between the outer pair, that is, having the last two planets very separated, apparently helps a lot to capture these planets in the 243. This favors a capture in the 243. Note that I'm talking about the separation of the last pair, because this is pretty much, there's little dependency on the separation of the inner pair. Now, we studied how these results, or how these captures varies when we vary planetary parameter and these parameters. So let's start with planetary parameters. What we can see here, that I varied a few parameters such as masses and initial orbits. We're going to talk about that. But what we will do is we will compare these grids with the previous grid, what we call the standard system, and we will see how little changes affect these results. So this is the standard grid, the standard model. Not the standard model, the standard grid. And what we can see, for example, we can start analyzing this case where we took the same systems, we ran the same grid, but with planets which have twice the masses. What we can see is that the capture region, that is the red region, moves significantly upwards. That is, the convergence, the capture regions shrinks a lot, which seems to suggest that bigger planetary masses actually prevent the capture in the 243. That made us think if smaller masses therefore favor the capture. And it's actually not that easy, not that straightforward. For example, here we have 3 mass cases. In the middle, we have the standard system, the classic 8, 9, 10 Earth masses. But in the left, we have 8, 9, 10 Mars masses, which are way smaller. I think one Martian mass is like a 10th of an Earth mass. And we can see that, again, as well, smaller masses seem to prevent a capture in the 243. And on the right, we can see the grid that we saw recently. Masses twice as large also seem to prevent a capture. So there seems to be like a sweet spot in masses between 1 and 10 Earth masses. Now, another thing that we noticed is in these two grids where we, for example, in the top, the upper right plot, we reduced a little bit the mass of the last planet. And we can see that almost every simulation got captured in the 243. Now, in the lower left plot, we actually increased the mass of the second planet. And we can see the same thing. The capture region grows. So what we take from here is that apparently a smaller mass difference between the second and third planet does seem to favor the capture a lot. In fact, I also want to mention that we start to see a few captures in the 473, that is the 0th order resonance right next to it, although they are still sparse and scattered about, while the 243 seems to produce this smooth region, this smooth capture region. Too important to be a first order resonance. In fact, well, as I just mentioned, we therefore a small mass difference between the last two planets seem to favor the capture. This is so. This is important in such a way that even a larger mass in the last planet, seems to prevent a capture in the 243. This is weird because when talking of planetary migration and resonant capture, you always want a heavier planet on the tail. You always want a heavier last planet. The heavier last planet will have a quick convergent migration, but the migration will be convergent. It will go faster than the inner planets. It will get close to them. They will get captured in a resonance, and you will have a resonant chain. If you want to create a chain, you need to put heavy planets last. But in this case, it's actually like the opposite. A heavier last planet, an 11 Earth mass last planet, seems to prevent the capture in the 243 at least. I have no doubt that all of these systems got captured in another resonance that we are not interested in this case. Well, in one last case, we also tested what happens if we, instead of fixing the last planet in 1 astronomical unit, we fixed it in 1.2 astronomical units. This is basically upping the scale of the system a little bit, giving it a bit of a bigger scale, because they have the same relative separation, the same period ratios, but on bigger orbits. And what we can see is that the capture region shrinks a lot. So I would have guessed that scale would not matter, but scale apparently does matter quite a bit. In fact, here we can see a smaller scale on the left, where we fix the last planet in 0.8, and we can see that the capture region grows a lot. But if we have a big scale, fixing the last planet in 1.2, the capture region shrinks a lot. You're getting an idea that what we are doing is sort of trying to come at a recipe of how to capture a triplet in the 243 resonance. Basically, we're trying to get a feel, because this is such a weird resonance in which we usually don't get captures. We're trying to explore it. But what we found here lastly was that a smaller scale seems to favor the capture. We will note again that captures in the 473 are only sparse, in contrast to the smooth regions of the 243. That is, there are very few yellow boxes over a smooth and wide red region, which is weird. Well, this last part will be very quick. It's basically the same, but varying disk parameters. And to go quickly over it, we find that the capture is actually especially sensitive to very small changes in disk parameters. In fact, what we change is that the capture is favored by a lower density disk. If you want to capture, put a very light disk. Yeah. The capture is also favored by a greater power law exponent. This is the density exponent, how the density distributes radially. The capture is also favored by a greater aspect ratio and a greater flare index, which is the curvature of the disk. In either case, captures in the 473 are again sparse and sort of loose, in contrast to the 243 resonance. So the 243 keeps on being like the stronger resonance for some reason. Okay, now coming to the real conclusion. This was still just a peek into a work in progress and a few simulations that we threw at the problem to explore it a little bit. We find that the 243 resonance generates a smooth capture region, while the 0th order one right next to it only generates a few scattered captures. And we also provide like a recipe on how to capture in the 243. We found that it is favored by all of these things. To not repeat them again. But okay, well, that's it for now. So thank you a lot for having me. I don't know how I did with time, but thanks.
Okay, Matías. Thanks very much. It was a great talk. Very interesting in several aspects. So now we are open for questions, comments. Anybody would like to make a question or a comment? Well,
They can be about the music as well.
Silvia?
Hi, Matías. Thanks for your talk. Very nice. I have a question. I don't know if it's naive. Did you compare or did you find a two-body resonance, mean motion resonance, in your last numeric simulations when you changed the parameters of the disk or the planets? They are still in this resonance?
Yes. Actually, that's a good question. That's a very good question that I forgot to mention, actually, because every one of these millions of they're not millions, but there are quite a few simulations. Every one of these simulations which arrives at the three-body resonance is actually captured in two-body resonance. We find that getting captured in this resonance, or even the other, means that you are captured. Like, let's take, for example, I think it's going to be clearer in this plot. For example, in this plot, getting captured in the 243 resonance always comes with the inner planetary pair being captured in the 3-2, which is this here resonance, and the outer pair of the triplet being captured in the 3-1. And this is the case for every single one of these boxes which gets captured in the 243.
All right. Thank you.
You're welcome.
Okay, thank you.
there are probably, I also want to mention, just in case, there are probably more captures for the systems which just continue downwards. They probably get captured in the 2-1, for example, which is like the next big one. But we cut it off. We are not interested in those.
Okay. Okay. Thanks.
Okay.
You're welcome.
I have a question related to the tides.
Yeah.
Yeah, that's very nice animation. You show the planets getting to the current positions. And my question is, what happens afterwards? Do that evolves?
Good question. Well, maybe probably yes. Probably if it arrived to this point via tidal interactions, as it probably did, or at least as it so promisingly appears to be, it probably keeps evolving via tides. The thing is that tidal evolution is actually very, very, very slow.
Yes.
Hundreds of millions of years. But yeah, maybe the system today is actually still going in these routes, but it's so slow that we would not notice it.
Okay, but my question actually leads to another one. So you can have some estimation of the lifetime of the system. How long ago it got to that?
I can't remember.
So you can get some kind of age of the system, this situation
Yes.
you have, since you have the time that it took to get to the current.
Probably, yeah. That's a very interesting case study. Probably, but the thing is that tidal evolution also depends upon many unknown parameters or loosely estimated parameters, which they would be, I think, a bit. It would have very big margins of errors when trying to estimate precisely the real age of the system. But yeah, I get what you're saying, and it's a very interesting.
The order there, just in terms of order of magnitudes. Okay.
No, yeah,
and,
I'm not sure. I'm not sure, but it's a nice question.
Yeah, perhaps you can make under conditions. So assuming this and that, the age would be like that, or things attached to each other. But I have another question related to the migration. When you showed the evolution of the same major axis of the bodies, I understand that you move the first one, then the others would be coupled by the resonance and would move. But in fact, the outer one, the sixth planet, it moves outward. The migration, it suffers a migration due to the resonance outwards in terms of semi-major axis. Is that what's happening?
Yes. It's like an outward tidal resonant migration.
Because that's weird to me. That's interesting. Because usually you have the inner body migrating, and then the other follows it. But to keep in resonance, somehow it moves outwards. That's really, at least it's new, completely new in terms of making a semi-major axis migration, not due to the tides, but due to the resonance. That's interesting.
Yeah. I find that interesting as well. Yeah, this is also like a result, like a geometrical result of the resonance itself. If one takes as an input that the first planet is falling, so you say, okay, the semi-major axis is changing, so the period ratios between 1 and 2 is changing. So then you take this blue dot and change it to the right. That if you assume that it will stay on top of the three-body resonance, you say, okay, if it moved here, now it's higher up here, and that actually gives you the x coordinate of the next triplet, which is the orange point, because they are all linked. And then the orange point also has to move. Then other periods have changed, therefore other semi-major axes have changed, and all of them depend on the slopes of these resonances. And if you do the math with these slopes, it results on the last semi-major axis going outwards, and it's all like a result of the slopes of this resonance. But yeah, it's pretty weird, especially talking about low mass planets migrating outwards. This is not migration driven by protoplanetary disk, but still that's like reserved for giant planets with protoplanetary disk.
Yeah, and it's driven by a weak third order, a weak three-body resonance.
Yeah, exactly. By a weak three-body resonance.
Yeah. So
yeah, but
really,
this would actually, but this would actually work even without it. Well, not the outward migration, just the global migration. But yeah, the outward migration driven by the weird.
yeah, the outward, that makes this so strange. Okay, but it's great result. Okay.
Thanks.
Thank you very much. So anybody else, any comment, another question? No? So I think that's it. Thanks very much, Matías. It was a great seminar and very interesting work, nice results, different results, and some art on it too. That was really nice to see the music on, to actually listen to the music of the
I had to include it.
Yeah, but that's great. That's great. That makes it even more interesting. Thanks very much.
Thank you a lot for inviting me. I really enjoyed it. Thanks.
Okay.